instant mathematics application. I want to introduce a little details of Professor Fadil Santosa. Okay? He has a bachelor degree in mechanical engineering, okay, and master and PhD degree in theoretical and applied mechanics. He graduated from the University of Illinois, Urbana-Champaign, and he has positions, postdoctoral positions at Cornell University, lecturer, and also assistant professorship in Cornell University. And then he moved to University of Delaware, and so he was assistant professor, associate professor, and a full professor in University of Delaware. And also he was the professor in mechanical engineering in Delaware. So he was both mechanical engineering and mathematical science. And he had professorship there. He joined University of Minnesota in 1995. Yeah, and he had a position as the associate director of Minnesota Center for Industrial Mathematics, and also associate director of IMA and deputy director of IMA. And now he's director of IMA. And he's a science fellow. Okay. And so far he produced the 16 PhD students. And okay, and he has also the several editorial board chairs. He's doing editors of Numerical Mathematics, Inverse Problems, European Journal of Applied Mathematics, Inverse Problem Imaging, okay, and several journals and several. Also, he published more than
2 papers.
Also, he wrote the 5 books. This is the end, I guess.
Yeah.
Welcome. Please.
Thank you. So, thank you. Thank you for the opportunity to come and give a presentation. What I was going to do was maybe take 10 minutes to introduce you to the institute that I direct, and use up some time so you don't have to follow the proof at the end of my other talk. So let me just quickly go over this, because one of my purpose for being in Korea is to engage more of the Korean scientists in activities at the IMA and to promote what we do. So let's go with that. So let's start with the vision of the IMA. Our vision is to be the world's premier mathematics institute where diverse talents address core challenges in science, industry, and society. So let me skip over. The IMA was founded in 1982. We just celebrated our 30th birthday. It is a National Science Foundation, U.S. National Science Foundation Mathematical Science Institute, funded by the Division of Mathematical Sciences of the NSF. We were, as I mentioned, in '82, we were established at the same time as MSRI in Berkeley. We are among the oldest institutes of DMS. As of today, there are 8 institutes. So there were only 2 institutes for the longest time, for the first maybe 15, 20 years, and then they added IPAM, then they added a few more like MBI and AIM and so on. The last one they added was ICERM, which is the one at Brown University. We all have slightly different missions and different focus, so we serve the mathematics community, all of us in our way. So I want to tell you a little bit about what we do. So let me skip this part. So what is our strategy? Our strategy is to be the information hub for the mathematical sciences to identify important research areas. We're not only actively look for research areas, but we also listen to what the community is working on and what they would like to see happen at the Institute. We instruct users of mathematics about new mathematical development. So we are very engaged with the users of mathematics in the fields like physics, chemistry, engineering, computer science, biology, as well as in social sciences. That's the area that we're trying to move towards. And then we gather the top mathematicians and scientists to discuss and work on these problems. So one of the outcomes that we would like to see is to bring together people that have never worked with each other before, so that they can come together at the IMA and do something new, and then they stay together and develop new research communities. Some examples of such communities that we have developed over the years are the ones in material science, for example. There's ones, even the math biologists that we have at the, right now, many of them have their start at the IMA. Not during my watch, it was before me. More recently, there's applied algebraic geometry that has also come from the IMA. The people doing areas of optimization that includes integer and they call it mixed integer programming also has their own community, and a lot of the community build-up was through the IMA. What is unique about the IMA and perhaps also with the other institutes as well is that we provide programs and environment that's very good for collaborative interdisciplinary research. We have workshops, we have seminars, we have places where people can gather informally and have discussions that are a little bit in a more formal way to start collaboration. We provide education and training for graduate students as well as undergraduate students these days, and we also play a role in increasing the public awareness of the importance of mathematics. So what we are is we're a visitors institute. We don't have any permanent faculty. There is nobody being hired permanently to do research in topic X or topic Y or topic Z. We're a visitors institute. People come, stay with us for a period of time, and then they go away. So we host long and short-term visits. We're on a postdoc program, and in a typical year we bring about 1,000 visitors to the IMA. On a given day, when there is no workshop, there are 40 people in residence. On average, and that's enough number so that it's like a small department, and they get together, they have their own seminars, they have one study group, and so on. When there's a workshop, the number goes up to about 110, 120, so we have an additional 80 or so people during workshops. Each year we focus on a theme, a topic. The thematic program is devoted either to a major subdiscipline of mathematics, for example, algebraic geometry and its applications, or a broad area of application and the supporting and related mathematics. For example, an application area could be imaging. Then we bring people in PDEs, people in image processing, people in signal processing, and so on together. So it's either a major area of mathematics or an area of application. Here are some of the things that we've done over the years since I've been in charge. We had a year on complex fluids and complex flows. This is a very applied area involving fluids. And then we had a year on simulating our complex world modeling, computation and analysis. This is sort of a numerical analysis and scientific computing year. Last year we had a year on mathematics of information. So this is this sounds like it's very current, but in fact we plan these things 3 or 4 years ahead. So when we ran the program in 2011, the Board of Governors, the Board of Science of the IMA was already discussing big data 3 or 4 years ahead of the actual program, and in fact 3 or 4 years ahead of NSF. So we had very good advice from the community about the areas that are important, that are upcoming. Right now we're running a year on infinite dimensional and stochastic dynamical systems. The year after that is, again, a major topic in mathematics, algebraic topology, and we're looking at scientific and engineering applications of algebraic topology. This is a very exciting year, and we're looking forward to that. 2014-15, we're looking at discrete structures, analysis and applications. This is discrete mathematics, combinatorics, theoretical computer science, and so on. So during the year, so example for this year, what I do as a director is I call up people and say, we're going to be running a year in infinite dimensional and stochastic dynamics, and don't you want to be part of it? So then I commit to a core group of scientists who will be at the IMA. Then we hire postdocs. We hire 8 postdocs a year to support the program. And then we also run workshops. So for this year, the workshops are as follows. We have 6 workshops planned. We already had one in dynamical systems in the studies of PDE. That one you can actually see the talks online if you're curious. Almost all our talks are recorded, videotaped. Last week we had a workshop on random dynamical systems. The next one that hasn't happened yet, and you can of course participate in this, is lattice and non-local dynamical systems. And then we have in January a workshop in stochastic PDEs. And then 2 workshops that are applied oriented. One is on atmosphere and oceans, and one on biological processes. Okay, so let me skip then. This one, the one I mentioned about algebraic topology, the organizers are Andrew Blumberg, Gunnar Carlson, he's a very distinguished topologist at Stanford, Graham Fan Chung, someone who does discrete mathematics and networks, and Robert Grice at UPenn, he's also a topologist and dynamical systems person. Susan Holmes is a statistician. Michael Mendel, a topologist, and then Konstantin Mishaikov, who works in differential equations and biological systems. As you can see from the makeup of the organizers, we really strive to make the program very broad and very diverse, and people from different areas are being, we're trying to recruit people from different areas to come into this year so that they can do some really good work at the IMA. Here's a quick list of the workshop of the applications of topology. You have data analysis. You have modern application of homology and cohomology. This includes, for example, exterior calculus, theory of ranking, and then also voting. And then you also have one on topological structures in computational biology. And then algebraic topology applied to dynamics. And then we have one on sensing and communications. And finally, geometry of networks and discrete matrix spaces. Now, not everything fits into the rubric of annual program. Sometimes we have really good ideas that come along, and we want to have to do something in it, but we don't have. It doesn't fit into the annual program. So we have a standalone workshops that are topical, and we call it hot topics usually. So there's one coming up in November. It's only a couple of weeks away. If you're interested, there's still time to go. If not, you can follow online. This one is on mean field games. It's a 2-day workshop, actually a 2-day short course. The main speaker is Pierre-Louis Lyons. We have also other activities. As I mentioned, we have a postdoctoral program. We hire people for the fall of 2013. We have the postdocs that participate in the annual program. We also have industrial postdocs. These industrial postdocs would spend half of their effort on industrial projects and the other half on their own research. We've had maybe about 100 of those over the years. We also have New Direction Visiting Professorship. These are for sabbatical, people on sabbatical that can be supported at the IMA. This one I would encourage your graduate students, if you're graduate students, to think about coming for this one. This is an interesting workshop that was originated at the IMA. The idea is that students would work in small teams of 6 people, and they work on a project that's defined by an industrial sponsor, or that's industrial mentor. They work in 10 days, and they have to come up with the best solution that they can in 10 days. And some of the outcomes of that includes papers, and sometimes they come up with really good solutions to the company, and they bring that solution back to their companies. But the workshop is open, so there's no issue about intellectual property. So this one is going to be in 2013. In February, you will see the list of projects on our website, and I hope that some of you will come. We've had students from Korea before for this workshop. We have summer schools. The next one is going to be at the IMA. The summer school is going to be on modeling of biological material. The other thing we've been doing also in the last couple of years is the ABLE conferences. This is an agreement that we struck with the Norwegian Academy of Science and Letters, and we hold a conference in honor of the ABLE Prize winner within the year of their award. So the next one is going to be for Zemeredi, and it's going to be from November 29th to December 1st. And finally, we also have New Directions short course. This is a short course where if you're not working in that area yet, but you want to get into it, this is a good way to get into it because it's a very intense 2-week short course taught by very, very good people on a topic that you might want to be part of research, to do part of your research in. The next one is going to be in June, and it's going to be on machine learning and statistical learning theory and machine learning. And the instructors are Bin Yu from UC Berkeley, a statistician, and David Madigan from Columbia University. We also have public lectures, and you can see some of our public lectures online. But again, as I said, IMA is really a community-run organization. We explore ideas with the community, and good ideas eventually emerge and become part of our program. So if you have good ideas, any idea, come and contact us. We would love to hear from you. So I'll skip that part, and this is my last slide. Visit the IMA, research, collaborate, and learn. So that's the first part. If there are any questions about the IMA, this is a good time to ask, because I'm not going to go into barcodes next. Any questions about the IMA? None at all? We've had many visitors. So Chang-Ok Lee was a visitor for 1 year, and Professor Kim was a postdoc at the IMA for a year. And you've visited for a workshop also in May. But come back and recommend IMA to your colleagues. It's a great place to go. So the next thing I want to talk about is about barcodes. So, and I plan to finish on time, so so don't worry. So this is, let me mention a little bit that this is joint work with Mark Iwan, who is now at Duke University. He's was a postdoc at the IMA, and Rachel Ward, who is now at a junior young assistant professor at UT Austin. You might well wonder why I'm doing research on barcode, because you go to the supermarket almost every day and buy things almost every day. And they use this laser scanner, and it's always successful, right? It scans the product, it tells you what price it is. And so why am I still doing this? Well, the reason why I'm doing this is because there are some barcodes that are very hard to read. For example, if somebody is shipping a package, the package gets rubbed and gets dirty in the truck, the scanner has trouble reading it. So these are the troublesome barcodes that I'm trying to read. The other kinds of barcode that are being used these days are for tracking parts in manufacturing. So many governments are now requiring manufacturers to keep track of where the life cycle of products, from the beginning where it starts out in a factory all the way to the end when you recycle it. So they won't be able to identify where that part came from, and they put barcodes in a lot of these things. But over the years, the use and the barcodes gets damaged. And in fact, sometimes you can't put the barcode on the part itself. You end up having to etch it using an etching on the metal. And that's very hard to read as well. Okay. So that's why there's still room to do research in this area. And the reason why I got involved in this was that a few years ago, I was giving a talk on total variation image processing, and somebody from a company that makes barcode scanners said, you have to come and understand what we work on and help us make better barcode scanners. So that's how I got involved. So the outline of my talk, I'll introduce the barcode scanning process, and this is probably, if you go away today and not understand anything else, I think at least understanding how barcodes are scanned would be useful, so that you will remember that there's mathematics behind it. It can be viewed as an image processing problem, a deconvolution problem. In fact, it's a kind of a blind deconvolution problem. But I will show that it's actually not the best way to solve this problem. The best way is to actually understand the language of barcodes and then come up with a new algorithm that is based on the language of barcode. And then I will have a quick discussion. So, introduction to barcode scanning. So here's the barcode on the left, and here's a typical scanner. This one is made by Motorola. And when you push the button, a laser light comes out and hits the barcode. The laser light actually moves back and forth on the barcode, and the laser shines and moves back and forth, and there's a light detector a light intensity detector on the scanner itself. So when the laser light is on the white part of the barcode, there's a lot of reflected energy. So it would register that there's a lot of intensity. When the laser is on the black part of the barcode, a lot of the light is absorbed. So the optical sensor would say that there is not much light being reflected. So the backscattered intensity is converted to voltage. Okay, and so you see something like this. When it's on the white part, you see a lot of signal coming back. When it's on the black part, there's a drop in the signal, and then it sees the white part again and comes back. But what you see here is that the black and white pattern on the barcode is telegraphed in the signal. So the signal actually it represents the barcode. The problem is that the width of the laser beam is just wide enough that you lose the resolution. You would like to see a very sharp drop when you go from black to white, but instead you see a gradual drop. And again, something similar here. Instead of a very sharp change in black to white, you see a gradual change. Okay, so that's the challenge. So the algorithm that is currently in use in a lot of these machines is very clever because of the fact that the distance from the scanner to the barcode is not fixed, depending on where you are and who's scanning. What they do is that they use the ratio of the width of the bars as a way of decoding the message. The message in this barcode is this 10-digit number. So the scanner, looking at this, looks at the width, that it estimates the width of the black bar and the white bar and so on, and then computes the ratio. The ratio then can be translated into these numbers that is encoded in here. Oops. Okay, so the ratios are converted into characters. Okay, there's also a camera-based one, like on your smartphone. The camera-based one does something slightly different. It takes a photograph. It identifies the region in the image that corresponds to the barcode, and then it does a barcode detection. This is a UPS package, but there's a special barcode here. They call it target barcode. And then there's some different bars. But this is probably the tracking number that's being recorded in here. And this is probably this information being stored here. Okay, so the idea is that you don't have to read those things, because reading often involves making a mistake. But using a scanner, you pick up those numbers instantly, talks to the computer, and then you can see that information is processed without any error. But sometimes barcode doesn't work because of the scanner, or because of the quality of the barcode, because of the quality of the printer. So that's where better algorithm is needed. So there are many kinds of barcodes. They are called symbologies. Symbology is like a language. So there's the most common one that you see. This is called the UPC, Universal Product Code. It was invented around 1970 at IBM. This is in almost all the products that you buy at stores. There's also code 128. This is used in the library books to store the information about the book, so that the book can be scanned as well. This one actually not only can store numbers, but it can also store ASCII characters. So barcodes are everywhere. There's a built-in error correction. In fact, if you go to this barcode, the UPC barcode, you go to a supermarket, you can erase one of the black lines, and the scanner will still work. So if you want to test it out, you can do that on the way home today. This guy has a barcode on the back of his head. I don't know why. But barcodes appear in nature. Look at the zebra. Zebra is a barcode. And this is true. So here's an article in Popular Science. New scanner tracks zebras' built-in barcodes. And there's a paper, Biometric Animal Databases from Field Photographs, Identification of Individual Zebras in the Wild, published in the IEEE. So this is very serious stuff. There's two-dimensional barcode. The one on the left is called PDF 417, which is one of the most common one. What it is to prevent fraud. When you have an ID card, you can you can always change the photograph or change the name. But if you have the data stored in this format, what your ID card will actually do is reproduce your photograph in a very rough way from this, and it also produce all your signature and everything else with using the barcode, because the barcode is a way of storage. So if somebody tries to fake an ID and it doesn't, and you use a scanner, you can actually see if that ID card is true or not, is correct or not. And there are all the different kinds, the QR code that you see a lot in advertisement. Okay, now time to do some mathematics. So that was the introduction. How is it a deconvolution problem? So we need to model this. One way to model this is to view the function that you're trying to recover, the black and white function, as a binary function. Let's call it z of t. It can only take on value of either 0 or 1. And we can put it in some class, let's say a bounded variation class, because we don't want barcodes that have an infinite number of transitions from black to white. Now the laser scanner that you use acts like a point spread function. As mentioned, physically what's going on is that the scanner is taking the average value of how much of the barcode is illuminated. So, so you can write this down as a convolution problem. And what it says is that here's the unknown barcode, which I have normalized to be 0 or 1, which meaning either black or white. 1 is black, say, and 0 is white. It's being convolved with a kernel. This kernel has a couple of parameters that I'm going to mention. One parameter, sigma, corresponds to how far you are from the barcode. The farther you are, the more spread there is of the laser beam, because the laser beam gets bigger when you're farther away. So this parameter sigma is how far away you are. Alpha is a conversion. You remember that I told you that the barcode scanner records voltage, which corresponds to the intensity of the light being reflected. So you have to convert from a function which is 0, 1 to some voltage, which is what you record here. Okay, so there is a conversion that needs to be also incorporated. And that depends on the lighting in the room. If it's very bright and if it's very dark, that scaling is different. There's also a noise that comes from the paper. The quality of the paper produces noise that is also recorded by the light detector. So the point spread function, the amount of blur depends on, as I mentioned, scan distance and the optics. Oops. And the simplest model for the blur for this kernel is the Gaussian. So you have a Gaussian function which is convolving this binary function, either 0 or 1, and this Gaussian is going to blur the image. The image is blurred according to how much how much spread there is. This is sigma, which corresponds to distance, and alpha is the voltage conversion from image to voltage. Okay, then that's also unknown because it depends on the ambient light and the environment. This is not a bad model, but it's not quite correct. A true model could be measured from a laser scanner, but this is a good surrogate that we can try to see how well we can do the inverse problems with just this. This is good for theory anyway. So as I mentioned, it can be measured and parameterized in the same way as I described there. So the deconvolution problem is you're given a noisy signal, you want to reconstruct a binary function and blur parameters alpha and sigma such that the recorded signal h is approximately equal to the blur function convolved with the binary signal. Okay, so you want to reconstruct binary signal, alpha and sigma, given h. Of course, you can formulate this as a least squares problem. So this is called a fidelity term. You're trying to fit the data. You're going to minimize over a class of u that's in BV and takes on values only in 0 and 1. And you're also going to try to find the parameters alpha and sigma that makes this quantity as small as possible. Okay, so what is known about this? There's a nice uniqueness theorem due to Esedoglu. It says that if there are two barcode signals that are noiseless H1 and H2, and the H1 is equal to H2, then the barcodes must be the same, and it must be from the same scanner. Okay, so the theorem is based on properties of the fact that G has compact support and it's smooth. So it uses it uses Parseval identity to prove. He also proposed a reconstruction method to reconstruct this image. Okay, so he came up with this formulation on how to reconstruct the image. He's going to minimize alpha, sigma, and u of this quantity called E. Let's think of E as energy. So he's trying to minimize the energy that's associated with the barcode image. The last part you already seen before. That's the part that says the data must be fit by the model. So this is the fitting part. This part is new. This part is doing a couple things. The first thing it's doing is that it's going to make the function to be either 1 or 0. Because w is equal to 0 when u is equal to 0, and it's equal to 0 when u is equal to 1. So it's this w forces is your preference for functions that are either 0 or 1. The first term is a penalty. The penalty is that is the cost associated with a transition going from black to white. Every time there's a transition, it is a counter that adds a cost to it. So what this is doing is that it's trying to fit the data, but at the same time making the function close to 1 and 0, and at the same time it's trying to minimize the number of transition in the function u. Okay, so it's a nice idea. This is actually related to a material science problem of solidification. It's called the Allen-Kahn energy, the first part. And the second part is a driving term which corresponds to your fidelity term, which you're trying to fit the data. You can write the gradient flow for this, steepest descent, and it looks just like this. It's not very hard. And you can discretize this and write an algorithm out, which is what I'll do in the next slide. So here's what he did, what Selim did. He wrote down the equation, and how he solves this problem is that if alpha is already known, which he's going to assume it's known, he starts with an initial guess, and then an initial guess also for sigma, which is unknown in G. He takes one step of this in the direction of y, one y step, which is a finite difference step. And then after that, he follows it up with a step to update sigma. Okay, so two-step algorithm. It's like an alternating direction algorithm. And then he terminates when it reaches a steady state. So you might wonder if it works. It does work. So here's a signal he's recorded or he's simulated, and you can see that there's a lot of noise in it. And you know, as I mentioned to you, that there should be a telegraphing of the black and white to the signal. This one is flipped upside down actually, so he has 0 where it's white and high signal when it's black. And his algorithm recovers pretty well the unknown function, binary function, or at least an approximation of it. The red one is the correct unknown. The blue one is what he reconstructs. So it looks pretty good, right? And if you are decoding, you can just use the half-point value as the transitions to calculate the width of the bars from black to white and white to black. So this works pretty well for this amount of noise, and if alpha is known. Okay, now it doesn't work all the time, but before that, somebody he posted his algorithm on his web page, and somebody programmed it onto a very cheap Nokia phone. And if you go to his YouTube site, you can see it working using his algorithm. So it scanned this barcode, and here's the number the same number that's being read by his phone. But there's a limit to its ability. What's happened here is that when there's too much noise and there's too much blur, this is the correct barcode. What his algorithm reconstructs is this one, and you can see that when there should be 3 bars, he sees only 2 bars. They're slightly wider, and there's a slight shift in each one of the bars. So this would not successfully decode. The barcode reader would not be able to if you use this image as a way to detect the width of the black and white bars, it would not decode properly. Okay, so the incorrect solution was found when the blurring is too high and the noise level is too high. And the determination of the scaling factor alpha was difficult in his algorithm. We did an analysis of this work and in the recent paper that we just published, and it reveals some theoretical limits. What we get is something like this. It is an error estimate. You get the correct barcode minus the reconstructed barcode as an error bound, is bounded by some things, and these things are exponentially dependent on the sigma. When sigma is big, the constant becomes huge, and it depends on the noise level to a funny power. So it doesn't have a nice dependence on noise either. Okay. So that's what the analysis reveals. So we need something better. So we need a new idea. So the first observation that I want to bring up here is that we don't care about the image. Why am I working so hard to reconstruct the black and white image when all I care about is the number that's being stored and hidden inside the barcode? Okay. So this insight tells me that the intermediate step of constructing the image, the black and white image of the barcode, is really not necessary. If I can circumvent that part, then I can go directly from the encoded data information to retrieve the encoded information directly from the signal. So this is a new kind of inverse problem. I call it inverse problem for words. Okay? Before it was inverse problem for images. This is inverse problem for words, because word represents in coding a sequence of letters or numbers, and that's what all I care about is a finite sequence of letters and numbers that I want to reconstruct from a signal. I don't care if there's an image associated with it. All I want to make sure is that I can reconstruct the word. Now, because this is a word, there's a huge advantage. A word is a finite number of unknowns. You know, let's say you have 12 digits, and each one of them can be either 0 or it's a digit that each digit is either 0 to 9. So there's a finite number of unknowns. So it's a discrete state. It's a finite state machine that I'm trying to recover from the signal. It's much easier to solve this problem than to solve the image processing problem, because the image processing problem in principle has an infinite number of unknowns. So, but to be able to accomplish this, I have to understand a little bit the language of barcodes. And this is where it gets a little bit messy but fun. I think you'll appreciate that barcodes are quite subtle. So the problem feature is the following. I have a word that's hidden inside a barcode. The word is related through a dictionary to produce a binary code. Okay, so you have a finite number of unknowns here, the ASCII characters. There's a translation from ASCII to binary. And the binary code itself is finite length. Okay, and it's through a dictionary. Okay, now what is this used for? This is used as an instruction to the printer to print the barcode. Every time I see a 1, I print a black bar. Every time I see a 0, I skip. See a 0, I skip, so leave it white. And I see a number 1 again, I print a black bar. If I see a sequence of 3 1s, I print black bar, black bar, black bar. So it's a black bar of width 3, and so on. So this is a printer instruction, and it produces the barcode. And once I have the barcode, I have the old model of the convolution to produce the signal. Okay, so what I would like to be able to do is to go from here to the word. Okay. Before, what I was telling you was, I'm going to ignore the fact that there's a dictionary and there's a whole world that translates the word to the barcode. I just want to go from here to here. I want now to go from here to there without really thinking about this part. Okay, so let me illustrate this with the UPC barcode. It stores a 12-digit number. The encoding procedure is very straightforward. you convert a number to a binary sequence according to a specified rule. So, for example, if you have a number 4, you replace this with a 7-bit binary code, 01000011, which, when it's sent to a printer, it leaves a white bar, it prints a black bar, leaves 3 white spaces, and then prints 2 black bars because of the 1-1. There's left digits and right digit. If it's on the right side, the right 6 digits, the bits gets flipped from 1 to 0, 0 to 1. And so the barcode would just change in color. Whatever was white here becomes black. Whatever was black becomes white. Okay? So this is how the 12 numbers are hidden. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. In between, they put sort of throwaway signals so that the barcode scanner knows that it starts and ends. So there's a start, 101, and an end, again 101, and then the middle part, which is this one. Okay, so the whole thing is a binary sequence of length 95. Give me any number, it will produce a sequence of length 95 of zeros and ones, which is used as a printer instruction to print the barcode. Okay, so that's the dictionary. So here's an example of a barcode using that dictionary. So there's the start, the end, there's the middle. This is the number 1, you can see it right there. White, white, black, black, white, white, black, and so on. Okay, so this is a barcode. So in fact, if you copy this, you can go to a store and you can look at, you can read the barcode numbers if you wanted to. Of course, why would you do that? You have a scanner to do it. So each digit is encoded in 7-bit, but very constrained. In fact, it's overcoded. They're actually using coding theory to do error correction. The entire bar has 95. The entire barcode has 95 bars. And about the code, it's a 12-digit number. It's a finite state machine, right? You're trying to recover the state. There's a special structure for the error correction that's built in. There's a checksum, which makes the number of state relatively small. This checksum is just to make sure that if one digit doesn't get read, you can reproduce that digit by looking at the checksum. So let's think of this as an inverse problem from the word to the binary code. From the word to binary code is just the sequence that I told you about before. Okay? So you start with a 12-digit number. You concatenate the following, starting out with the start code 010, and then the left digits. There's 7-bit 01 code, and then you concatenate, you go to the middle, and then you lay out the 6 right digits in binary, and then you end the code. So that's the forward map from the word to the binary sequence. So you get a binary sequence. Once you have a binary sequence, I want to go to the signal, and here's where it goes. So you convert the 95-bit binary sequence into a black and white bar of some chosen width. That's the printer instruction. And there's your barcode. And the barcode is a binary image, which is what we worked with before. The binary image is now convolved. Okay, so you have z of t, which represents the binary image. You now convolve, which is the same old model. Okay, so now I have the whole sequence from the word all the way to the binary sequence, all the way to the signal. Okay. And after you discretize, or at least in terms of operators, you can write it out as h is equal to alpha. Remember, alpha is a scaling, so I just put it outside. And g of sigma times operating on z, which is the binary function, plus some noise. And that's what the signal might look like if it's a true barcode. Okay. All right, so now I have the procedure all the way from the word that is hidden inside the barcode all the way to the signal. Okay, now I need to think a little bit. I need to think about how to represent the unknown in such a way that I can actually solve this problem. I now only have I only lay out the procedure of how the forward map going from word to signal looks like. Now I need to represent the unknown as in a pretty peculiar way that allows me to solve the problem. So this is the algorithm that I'm going to talk about. So the dictionary, let's go back to the dictionary. I want to be able to write down the unknown so that, remember the unknown is a word. From the word to the binary sequence, I want to write it out as a linear operation involving a matrix. Okay? So this is the whole thing is about this. Remember that let's say B represents the unknown 12th digit that I'm trying to decode from the barcode. I write it out in the following way, which is the rule for laying out the UPC barcode. Start, N, and middle, and then the 6 digits and the 6 digits. That's the 12-digit number. B has only 12 unknowns. Okay, the unknowns can only, each unknown can only be 0 to 9. Okay. So the binary code is a 95 length sequence of zeros and 1. 0 means white bar, 1 means black bar. I want to be able to write this. See, the binary sequence is equal to some thing times B. Okay, how do I do this? I do this as follows. I look at the lookup table and I tip it on its side. Okay, this is the lookup table for the left digit for number 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. If I want to take number 4, if I want to produce the binary sequence for number 4, I want to pick up the 5th column, sorry. And the same in the right. If I want to pick up number 4, I pick the 5th column. So my unknown is going to be, if the number is 5, and if the number is 4, I want a vector that only picks out the 5th column. That's just very simple to do, right? You can just write it out as a length 10 vector with everything 0 except the 5th entry equal to 1. Then it will pick out that column. We always need the start and end. So what I do is I write the whole thing out as the following matrix. This is the matrix A. Okay, so I always need to have E, M, and S. That's the signal to the scanner that you're starting and ending, and you're in the middle. And then you have all these matrices L and R. So the unknown is going to pick columns from these guys and pick columns from these guys. And each one of those column picking vector is a bunch of zeros with a 1 in the place where the digit you want to pull out is. Okay, so here's what it looks like. So the unknown, for example, for the sequence 0, 1, 2, 3, 4, 5, etc., would look like this. Would have to have this because it has to have a start sequence. If it wants to pull number 0, it must have a 1 and then followed by 9 zeros. If it wants to pull number 1, it puts a 1 in the second place and then 0 everywhere else, etc. Okay? So now I have what I need. If my unknown is represented this way, then I have the matrix A, which I wrote down in the previous slide, and this is the binary sequence that I'm going to use as an instruction to the printer. Okay, so we're almost there. So the unknown is a very convenient representation. It's called a very sparse representation because it's mostly 0. And its significance is that wherever the entry is, it tells you what digit is being represented, being pulled out from the dictionary. Okay, so this vector has 12 components, which has each one of the component is length 10, and only one of the entries is non-zero, which is a 1. Okay, so now I'm almost there. Now I create the binary image. The binary image is to take the binary code and extend it. It's an extension operator to produce a function, basically. And that's a linear operation as well. So now I go from the binary sequence to a function, z, which is a piecewise linear function taking on values of zeros and 1. And so the entire problem looks like this. The unknown has a very specific and very special structure because of the way I constructed it with the dictionary. I have the extension operator, which is known, because that depends only on how wide I want the barcode to be. And then there's the convolution, the blur from the laser of the scanner. So the inverse problem is now, given H, I want to determine B. Do I care about alpha and sigma? Yes, I do, but I need also to determine those. Okay, so it turns out that it doesn't, the algorithm that I'm going to describe doesn't seem to care about sigma very much, but it does care about alpha. So alpha has to be determined separately. So the B vector that I'm trying to determine is very special. It's a long, skinny vector, mostly zeros, with only ones. Every 10 block has a 1 in it, and so on. Okay? So the best algorithm for doing this kind of work is, let me skip that one, is a greedy algorithm. Okay? So I start out by guessing a value of sigma. Remember that I had to determine alpha, which was very difficult in the image reconstruction problem. But here it's actually quite easy. Because I know part of the signal corresponds to the start, the end, and the middle, I use that part of the signal to determine what alpha is. And once I know alpha, I apply a greedy algorithm to recover one digit at a time. Okay, starting from the left to the right. So it's sort of a discrete algorithm, a discrete approach to a problem that involves only a discrete number of unknowns. So this works for a large range of sigma, and I will show you a couple of examples. Here's a barcode that was reconstructed using this algorithm. This is the signal. This signal is big enough, even in this simulation, that no known algorithm would be able to recover this. We were successful in recovering this. The correct amount of blur is 0.8. Sigma is equal to 0.8. A is equal to 2. There's 20% of noise. You use the algorithm with sigma being 20% off, equal to 1. So I'm just guessing the value to be 1. And then alpha is calculated from the part of the signal that corresponds to the middle, the beginning, and the end, and we calculate it to within about 0.5%. And then the barcode is reconstructed perfectly. This is another example where I underestimated the value of sigma, and it still reconstructed it perfectly. Okay. So I gave you an algorithm, but what can I prove? So what we can prove is the following. The first theorem that we can prove is that if the scanner parameter alpha and sigma are known, let's pretend that they're known for a minute, we can show that if the blur, sigma, is not too excessive and the noise level is not too large, the algorithm converges to the right solution in one step, in one iteration. Okay, the key to this is the observation that the matrix involved is nearly block diagonal. So there's the matrix that is involved looks like this. There's an overlap region here and here, but what you can show is that if the energy in the overlap region is small in comparison to the energy everywhere else, the algorithm will work. So that's in place of the proof. I'll just hand wave and say that this works because of that reason. We can also show that the reconstruction is insensitive to small errors in sigma and alpha, which is exactly what we want, because if we don't know alpha and sigma exactly, we want it to be able to still reconstruct the unknown. Okay, the proof hinges on the property of this matrix, which has this block diagonal structure. I sketched out a proof, but I don't think I'm going to go through it, but it's basically has to do with exactly what I just described here. There's an overlap region, and you're going to say something about the energy in the overlap region of that matrix is small in comparison with energy differences of each one of the columns in the non-overlap region. And then you can do the algorithm recursively for all the characters that it's hidden. So I'll skip that proof. And finally, a discussion. So I describe a barcode decoding problem. I gave you a long introduction about how it works. So now, the next time you're at a store, you'll remember this talk and you say, yes, there's mathematics behind that. And then the problem can be viewed as a deconvolution problem for a binary image, can be viewed as an image processing problem. But it's not the best way to do it, right? If we have the phase field algorithm that Salim proposed, in fact, the better algorithm is to exploit the words structure of the barcodes and turn this into basically a finite discretization problem, almost like a combinatorial problem. So I describe a problem of finding a 12-digit number from a signal from a UPC barcode. And then I showed you a greedy algorithm with very good properties that can be proven to have good properties. This part of the work has appeared in the Journal of Imaging Sciences. And then there's a bunch of to-do lists here. The detection of the edge of the boundary of barcode is actually essential in the algorithm that I use. So I need to know when in the signal when the barcode's edge gets started and where the signal from the end of the barcode is, because I need to shoehorn a barcode inside the signal, and that makes things work. I'm also working on different symbologies. This is in progress. Different symbologies mean different dictionary. And in particular, some dictionaries like the code 128 does not restrict the number of characters to be 12. In fact, it's indefinite. So that's part of the challenge, is to detect how many characters are inside it so that I can shoehorn the algorithm inside and then do the greedy algorithm to recover each one of the characters. So that's not done yet, and we have some ideas about how to approach it, but none of them are very good right now. And finally, we are also extending this with my student Madeleine Schreier, extending this to a camera-based scanner, where we're looking at it as a classical, in the classical image processing, it will be called super resolution. You got a very badly sampled image and you're trying to super resolve it so that you can see the edges. Well, we're not going to use super resolution directly. We're actually going to use the dictionary to try to help us to do the super resolution. And we have just begun to get some results with that, and that's what's going on. Of course, eventually I would like to be able to do two-dimensional barcodes as well, but that's a little bit further down the road. So that's what I want to say, and I hope that if nothing else, you'll remember the next time you buy something at the supermarket that barcode is important and there's mathematics behind it. Thank you so much for listening.